Hello everyone, I hope everything is fine. So in today's simulation we are trying to talk about activation energy, and in particularly we are using COMSOL to find the kinetic Arrhenius parameters using a parameter estimation toolbox of COMSOL. So before I start to talk about a little bit about energy and chemical reactions. So what is chemical energy? The energy stored in a chemical bond of a substance is called a chemical energy. And how do the reactions occur? Reaction always occur when there is a change in energy, in chemical energy. And how this is happening is by making bonds and breaking bonds. Making and breaking of the bonds involves chemical energy or chemical energy changes. So what is activation energy? The energy required to break the bond in a reactants for a chemical reaction to occur. So in order to a chemical reaction to occur, the bond has to be broken, and the amount of energy that is required to break the bond is called activation energy. As you can see from this illustration, the amount of energy that is required to break the bond is basically give you an indication of how much is the activation energy that you require to break the chemical bonds between the reactants. So there are basically two steps in breaking and making of bonds or chemical reaction. Step number one, energy must be supplied to break chemical bonds for the reactants. This is the first step. And the second step, energy is released when the new chemical bonds are made in the product. So in this context, a reaction is exothermic if more energy is released than supplied, or if more energy is supplied than released, then the reaction is called an endothermic reaction. So based on the type of energy, which is heat, changes involved in chemical reaction are classified as exothermic reactions or endothermic reactions. So exothermic means energy is released, where exo in the exothermic term is called exit, and the example is burning of gasoline. And in endothermic reaction, which is energy is absorbed, and endo means into, example cooking of pancakes. So in endothermic reactions, this is a diagram which shows the amount of activation energy required to break the bond. So as you can see from here, the activation energy is released used in a bond breaking. That is called activation energy in this particular case. And in this context, you can see when the product is formed, energy absorbed in a reaction. So energy is released in a bond making. So endothermic reactions, more energy is taken in to break the bonds in the reactants than released by the bond before formed in the product. Therefore, energy is absorbed. In this particular case, heat energy is taken in, temperature of the substance drops in endothermic reactions, and product feel cold. You can see from this illustration. And in endothermic reactions, normally we represent endothermic reaction in this kind of you see the endothermic reaction written in like this, where you have reactants, you need energy and to form product, or you have reactants, you need a heat so that it can give you a product. In other contexts, in other terms, exothermic diagram you can see from here, the activation energy is used in the bond making. And this difference shows the energy released in the bond making. And so what is exothermic? So in exothermic reactions, more energy is released when the products were formed than the energy was used to break bonds in the reactor. Therefore, a net release of energy is shown here, which is activation energy. So in this context, the heat energy is given off. In exothermic reactions, the temperature of the substance rises and you will feel the product is very, very hot. So in exothermic reaction, you may see an exothermic reaction written like this, where you have a reactants will go to the product, plus it will give us some energy, or you have a reactants, it will go to the product side and will give us some heat, or heat is produced. So let's jump into today's example. What we are trying to achieve today is we have a benzene diazonium chloride, and a gas decomposes to benzene chloride and nitrogen according to this reaction. The reaction is first order within the rate, which is shown here. So in this particular case, you can see K is represented by this term, and in above, the value of the A is the frequency factor, and the unit in SI units are 1 per second, and E is the activation energy in the unit of in SI units are joule per mole. This particular example is taken from a book H.S. Fogler, Elements of Chemical Reaction Engineering, 4th edition, page number 95. So this particular example is taken from this book. So what exactly is the problem? The problem is, in order to evaluate the Arrhenius parameter A and E, a set of experiments was conducted using a perfectly mixed isothermal batch system with a constant volume. The concentration of benzene diazonium chloride was monitored as a function of time for a temperature. For example, in this particular case, we have different temperatures are used. Experimental temperature are used to find out the concentration of benzene dichloride. We can start with 313 Kelvin, 319 Kelvin, 323 Kelvin, 328 Kelvin, and 333 Kelvin. These are the different temperature. On these temperature, we need to find out what is the concentration of benzene. Change in concentration of benzene dichloride was monitored. The model is COMSOL optimize A and E at this temperature. So we use the model in COMSOL, which is basically used to optimize A and E at these temperatures with the parameter estimation feature for simulation utilizing the isothermal constant volume batch reactor. So the parameter estimation solver is more efficient in COMSOL in finding the optimal parameter set if the model experiences similar sensitivity with respect to changes in parameter value. In this problem, a parameter AEX is therefore defined. You can see from here this example, this is the rate constant. You can see here this is the equation of Arrhenius equation. In this particular case, A is nothing but the exponential of AEX. In this problem, a parameter AEX is therefore defined, that is to be estimated together with activation energy E, such that the rate constant is written as these particular terms. So we will use COMSOL Multiphysics. So what is, before we start doing a simulation in COMSOL Multiphysics, we need to talk about a little bit what is COMSOL Multiphysics and how we can use this. So COMSOL Multiphysics is a finite element analysis solver and simulation software, FEA software package for various physics engineering applications, especially coupled phenomena or multiphysics. COMSOL Multiphysics also offers extensive interface to MATLAB and its toolboxes for a large variety of programming, pre-processing, and post-processing possibilities. The packages are cross-platform, can be used by Windows, can be used in Mac and Linux. In addition to the conventional physics-based user interface, COMSOL Multiphysics also allows for entering coupled system of partial differential equations. The physics-based modules augment the core physics interface of COMSOL Multiphysics and provide additional physics interface for electrical, mechanical, fluid flow, and chemical applications. So what COMSOL Multiphysics includes? It includes, for electrical application, it has AC/DC, RF, wave optics, MEMS, plasma, and semiconductor modules. In mechanical application, it has a heat transfer, structural mechanics, non-linear structural materials, geomechanics, fatigue, multi-body dynamics, and acoustic modules. And in fluid flow applications, we have CFD, mixer, microfluidics, subsurface flow, pipe flows, and molecular flow modules. In chemical application, we have chemical reaction engineering, batteries and fuel cells, electrodeposition, corrosion, and electrochemistry modules. In multi-purpose application, we have optimization toolbox, which we are going to use today. And we have different material library for different substances, and we also have particle tracing module. Similarly, we have the interfacing application. We can link COMSOL with different modules. We can link them with MATLAB. We can link them with SolidWorks, and we can also link with different packages, even with Excel also. So let's jump into today's simulation. So the first thing that you see when you open COMSOL is the model wizard and the blank model. So we need to click on the model wizard. And since in our case, in an example, we don't have a geometry, so we click on 0 dimension. And in this case, since we are working with the chemical reactions, we need to click on chemical species transport and reaction engineering and click on add to the physics interface. And we click on study. Since our we have experimental data which consists of time and concentration, so we can click on time dependent study. So we can click on done, and we need to click on more in this case. So the first thing that we need to see here is we have a model builder, we have the setting, and we have a graphical interface, and then we have different tabs on the top. Since in our case we are basically trying to optimize two parameters. So the first thing that we need to define is the initial values of the parameters. So we click on the global definition and parameters, and here we have the option to add those parameters manually, or we can add them by using a file, a text file or a CSV file. Since we have these parameters in the CSV file, so we just go and locate them. So click on this file button and click on activation energy parameters and click on open. So these are the parameters that we have. We define the name, the AEX, the expression. We can write the expression, or we can write the values directly, which is 49. Value is 49, and this is the rate constant parameter. Since similarly we have the initial concentration, which is mentioned here is 1000, and this is the name that we need to use. We can use anywhere wherever we need in a simulation. So that's why it is very handy for us that we can use this information later on. So we can define them first and then we can use them later on. Similarly, we have activation energy, the starting value, which is the initial value, which is mentioned here. And similarly, we have the temperature, the initial temperature, which is mentioned here. And all these parameters are defined by these names, which we can access in the simulation. The first thing that we need to see, we need to bring those parameters in the simulation. And the second thing, since we have a chemical reactions, we need to click on the reaction, and we need to click on reaction. And on this side, in the formula bar, we need to write on the chemical reaction, which is in this case is nitrogen. After you write down the formula, you need to click on apply, and all those information related to this reaction will be accessible here, like the reaction type, the reaction rate, and the rate constant, which we can later on use Arrhenius expression. Before I can go to the Arrhenius expression, I just want to give the initial values. If you remember, in our parameter section, we already defined the initial value. So we just copy this name, and you can just paste it here. This is the first thing that we need to do, and after we define this, we need to click on reaction engineering and click on parameter estimation. So here we have two parameters we need to optimize. First is AEX, and the starting value is already is 49. And the second parameter, we need to click on this plus icon, and we need to define this activation energy, which is in this case is 1508.3, and inside the bracket we can write the units. So after we define this one, now we need to add the experimental data that we have. So how to add experimental data? We need to click on direction engineering again. We need to click on attributes and click on experiment. This is how we can bring the experimental data. Again, the experimental data that we have is already defined inside the CSV file, which I will show you in a minute. Let's go to the. So this is the different experimental data of different temperature, which is mentioned in the CSV file. I just open one of them and want to show you what you will get in this data. So here you can see we have a time and we have a concentration at this time and concentration at this isothermal temperature at this particular temperature data information which is mentioned here. Similarly, we have the same data at different temperature which is also mentioned, which we already have. So we need to bring this data back to the in experiment number 1. So how we can do this? We can click on browse section and we can click on this first file and we can click on import, and here we write the name of this model variable, which is C underscore pH and 2. I just want to copy this one because I want to use this again and again. Copy this one, and once you add this, you can come down, and here we need to add the parameter. This data is basically at 313 Kelvin. So click on this plus icon, and here in the parameters, which parameter? So we need to write temperature, isothermal temperature, and the value of isothermal temperature is 310. So this data is basically at 310 Kelvin. So we need to define this. So after you do this, you can again go to the attributes and click on experiment again. Here we need to add another data. So again, for this data, we again need to click on browse, click on the second file, import, and here we write the variable name. You can go down, we click on plus icon, and the parameter that this data is on is temperature. At what temperature this data is on 319 Kelvin. Similarly, we can click on, again we can click on parameter estimation, click on attributes, click on experiment, again browse, 323. So we will paste the variable, go down, click on the plus icon. This is at this temperature, and this one is 323 Kelvin. Again click here, click on the attributes, experiments. We have 5 experimental data points, so we need to add all of them. Click on browse, click on 328, import, give them a name, come down and add, click on the plus icon and add the temperature, and this one is at 328 Kelvin. And the last one we have is, okay, we add to browse, we can add this one at 333, click on import, paste this one here, go down, click on the plus icon, change this to temperature, and this one is 333. So we have added all 5 temperatures. After this, we need to click on reaction engineering, and in the reaction engineering we see this energy balance. So obviously our temperature is changing, so instead of just writing a fixed temperature unit, we can write here T underscore ISO, which we already defined in our parameter section, which is this one. Okay, so we define this TSO. Then we need to click on the reaction itself, and now we need to go to the Arrhenius constant. We need to check this Arrhenius expression. In the first one, since we have a little bit change in expression, we might write exponential EX, and for activation energy we write E, which we already defined in our parameter section. Okay, then we need to click on the study, the time dependent study, and in the time dependent study, the thing that we need to change is the output time. So we need to start from 15, go all the way to 5000. Right, after this we need to click on study, we need to click on optimization and click on optimization tab, and here we need to change the optimization solver information. The method that we are going to use is Liebenberg method, so we need to click here, So, and then again, after clicking this one, we need to click on the solver and we need to click on show default solver. So once you can see the default solver, you can just open this node, click on the optimization solver, click on the time dependent part of this one, click here to open the output, and you can see some of the things are checked here. Then we can just leave it like this, and then we can click on compute. The process will take some time because it is starting from 50 and going all the way to 5000, so it will take some time. So we will wait for the simulation to finish. Right, so you can see at different temperature we have the concentration profile, which is mentioned here, and since we also have the convergence plot, how this is converging. You can see here by the time it is with different iteration, it is converging with a low error. Right, so basically what we need to see is how at each experimental data points, how our model is behaving. So we need to click on different groups. So in the results section we have different experimental groups. Experimental group number 1, now you can see here it is not showing the correct order. So what we need to fix this. So the first thing that we need to see here, we need to click on this group and we need to rename the label, and here we can call this one experiment group 313 Kelvin. That is the first thing that we need to change. Second, we need to click on the title and we click on none. We're not giving any title. We need to click on x-axis and check this one and write time. Similarly, on y-axis we need to write and this is HTML, writing some HTML here, and the units. So this is written here. Then we need to click on this arrow and we click on experimental data, and in this experimental data section we need to table graph, and we need to click on the legends and yeah, need to click on legends, and here we need to click on manual, and the legend that we need here is experiment at 113 Kelvin. So you can see here the legend is shown up here. Then we can click on global, and in the global section we can see here we have the parameter section. So we click here parameter, we can click on from the list, and this one is for 313. On the y-axis we need to click on replace expression part, Here we need to click on reaction engineering, and what we need on y-axis is our concentration, which is this one. It's a double tap, so it will change here. Then we can come down, and on x-axis we click on again the same thing. This time we need to click on solver and time, and we can click on double click. Right, after you do this, you need to come down to the legend section. First you need to click on legend and click on show legend, and immediately you can see here the line shows the prediction, whereas the dot or the markers you can see here is the experimental data points. We need to change the name here, so we can click on the prefix, and here we can write simulation at 313 Kelvin. You can click on plot. Now you can see here the information is updated. Right. So this is how we can see the results of prediction and experimental data. We can use this information to find out the parameter A, the frequency factor, and the activation energy. I will show you that one later on. First we need to fix, this is our experimental group number 1. Same thing we will do with experimental group number 2. So for experimental group number 2, again we need to write we need to click here, we need to write here experiment group 319 Kelvin, and the title I will click on none. For X label I will write this again time second, and for Y we can write here and sub to close sub write CL, write the units, so we can write these units. Now we can go down and we can see legends, or we can just open this one, click on experimental data, go down to the legend, and here we need to write experiment group 319 Kelvin. Right. So we write this as manually, become manual, and here we need to write the experiment group 319, separated here. Click on global. In the global section you need to click on global 1 setting, go to the data section, this one you need to click on from the list, this one is 17, you go down, you click on expression, this one will be concentration, you go down, this will be time, you go down further, let me manual, and we delete this, and we need to write here what we need to write. We need to write simulation at 319 Kelvin. And click on show legend. Now you can see the comparison, and you can see the prediction and experimental results are very near to each other. However, what we need to see is what is the value of A and E that we are getting. So we are done with the experimental group second. We click on the third group. Again, for the third group, we need to click here and we need to write experimental group. Group 323 Kelvin. The title type we will click none. X-axis again we need to write time into second. Y-axis we need to write yes, we need to write pH and right, so we write this, yes, and go down. Yes, we need to click on this small arrow, click on experimental 3 data, and here we need to go down all the way to legend, click on manual, and this one we need to write experiment at 323 Kelvin, and then we can click on global. First thing that we need to see here, we need to click on parameter from list 323, click on this expression, select the concentration, click on x-axis data, select the time, go down, show legend manually, and change this to simulation at 323 Kelvin. Again, you can see the comparison exactly matches each other. So this is it means like optimizer is working very fine with this experimental data. Similarly, we can click on the experimental group 4, and this one we can call this one experiment group 328. The title I will click on none. For X label I can write time, and for Y I copied already to this location. Okay, then we need to click on this arrow, click on experimental 4 data, go up, yes, we can click on legend, click on manual, and here we need to write experiment 328. Click on global, go up, change the parameter selection from the list to 328. go down, select the y-axis data, select this to concentration, go down, select the x-axis data to time, go down again, show legend manually, and here you write simulation at 328 Kelvin. Again, it's showing a very good comparison with experimental data. The prediction experimental data shows quite accurate. Then we could go to the last one, which is experimental group number 5. Here I can write this one, experimental group 333 Kelvin. Right, and then the title has to be none. On x-axis it is time second, and y-axis has to be the one which I already copied. Right, and then we can click on this, open this one, click on experimental 5 data, go down to legend, and then click manually, and here we write experiment 333 Kelvin. Click on global, go up, parameter selection from list is last one, which is 133, and we need to click on y-axis data, select the concentration, click the x-axis data to time, and for legend we need to click on manual, show legend, delete this one, and here we write simulation at 333. So you can see again the comparison show good approximation with both experimental data and the prediction. Right, after you do this, we need to click on the results, and after clicking on the results we need to click on this result here, click on numerical and click on evaluate all, and after you see that now you can see from here the activation energy that we have optimized based on experimental data is 36.9, and not activation energy, the frequency factor is 36.948, and the activation energy is 1.16 e to the 5 joule per mole. So this is how we are able to use COMSOL to optimize the activation energy and the frequency factor. I hope you understand today's simulation using COMSOL and how we can optimize the Arrhenius parameters. If you have any questions regarding this, please don't hesitate to ask. Thank you very much for listening. Take care. Bye.